Imagine standing beneath the light of 3 suns, one golden yellow, casting long shadows across crimson soil, another, a smaller orange companion, hovering just above the horizon like a jewel suspended in amber twilight. And finally, a distant red ember, barely visible against the alien sky, completing a trinity of starlight that no human eye has ever witnessed. This is Alpha Centauri, not as seen through a telescope, but as it might appear from the surface of an undiscovered world, orbiting in that distant system, a place so achingly close in cosmic terms, yet impossibly, unreachably far by any measure of human ambition. Alpha Centauri beckons to us across the void, a stellar lighthouse merely 4.37 light-years away, our nearest neighbour among the stars. When we gaze upon it in Earth's southern sky, the photons entering our eyes began their journey over 4 years ago, crossing an ocean of darkness so vast that numbers begin to lose all meaning. 4.37 light-years. It sounds almost manageable, doesn't it? A handful of years at light speed. Surely with determination and ingenuity humanity could bridge that gap. Surely the same species that went from wooden ships to spacecraft in mere centuries could find a way. But here is where the dream collides with the mathematics of reality. That seemingly modest distance of 437 light-years translates to roughly 25 trillion miles. 25 million miles. To put it another way, if the Sun were the size of a period on this page, Alpha Centauri would be located over 10 miles away. If we could drive there at highway speeds, never stopping, never slowing, the journey would take more than 40 million years. Even at the speed of our fastest spacecraft, Voyager 1, moving at about 38,000 miles per hour as it leaves our solar system, the journey to Alpha Centauri would require over 75,000 years. 75,000 years. When Voyager 1's journey would be halfway complete, humanity as we know it would not yet have invented agriculture. Tonight, we embark on a different kind of voyage, not one of hope and wonder, but of brutal, unflinching mathematics. We will explore every dream, every clever solution, every technological miracle humanity has proposed to reach Alpha Centauri. Nuclear pulse propulsion that would ride the shock waves of atomic bombs, antimatter engines that promise relativistic speeds, generation ships where civilizations would live and die in transit, suspended animation that would freeze time itself, light sails pushed by lasers more powerful than nations. We will examine each one not with cynicism, but with honest physics, and one by one, we will watch them crumble against the immense indifferent wall of interstellar distance. This is not a story of human limitation. It is a story about the universe itself, about the fundamental laws woven into the fabric of space-time that conspire, almost deliberately, to keep us locked within our stellar cradle. Einstein's equations become prison bars. Energy requirements balloon into absurdity. Time dilation transforms journeys into paradoxes. The speed of light stands not as a challenge to overcome, but as a cosmic speed limit enforced by reality itself. As you settle in tonight, perhaps drifting towards sleep, let these impossibilities wash over you. Let the scale sink in slowly, the way starlight soaks into darkness. This video is designed to be both mesmerizing and mathematically rigorous. Perfect for those quiet hours when the mind wanders among the stars but the body remains firmly anchored to Earth. Before we venture deeper into this cosmic prison, I'd love to know, where in the world are you watching from tonight? And what time is it where you are? Drop a comment below. It reminds us that even though we're scattered across one pale blue dot, we're all gazing upward at the same impossible distances, dreaming the same impossible dreams. The truth we will uncover is not comfortable. It does not end with triumph or a roadmap to the stars, but it is profound. For in understanding why Alpha Centauri remains beyond our reach, we begin to grasp something deeper about our place in the cosmos, about the Fermi paradox, about why the universe seems so hauntingly silent. Perhaps the great filter is not nuclear war or climate catastrophe. Perhaps it is simply distance itself. An ocean so wide that intelligence, no matter how advanced, remains forever bound to the shores of its birth star. So let us begin this journey, not outward into space, but inward into the cold mathematics that govern it. Let us explore the tyranny of distance, the energy problem, the relativistic nightmares that await any vessel daring to approach light speed. Let us confront the generation ship paradox and the uncomfortable truth that humans ourselves, fragile and short-lived, may be the fundamental barrier to interstellar travel. Alpha Centauri shines tonight, as it has for billions of years. 3 suns, impossibly far, impossibly close, forever out of reach. And in that distance lies a truth we must accept if we are ever to understand our cosmic solitude. Let's begin. Alpha Centauri glimmers in our night sky, a pinprick of light so faint that most of us never notice it, among the thousands of other stars scattered across the darkness. It appears close, almost reachable, another point in the celestial tapestry that surrounds our world. But this closeness is an illusion, a trick of perspective played by the universe itself. Alpha Centauri is not close. It is incomprehensibly, devastatingly far away. And to understand why reaching it is impossible, we must first confront the tyranny of distance itself. 4.37 light-years. This is the distance that separates us from our nearest stellar neighbour. Written in numbers, it becomes 25 trillion miles or 41 trillion kilometres. These figures roll off the tongue easily, but they mean nothing to the human mind. We cannot comprehend them. Our brains evolved to understand the distance between trees, between villages, between horizons we could see with our own eyes. We can imagine walking across a continent or sailing across an ocean. But 25 trillion miles. The number is so large it becomes abstract, a mathematical symbol rather than a distance we can truly grasp. Let us try to make it tangible. Consider the distance from Earth to the Moon, roughly 240,000 miles. This is a journey that took humanity's Apollo astronauts 3 days to complete. It represents one of our greatest achievements, a voyage celebrated across generations. Now imagine travelling that same distance not once, but 100 million times. That is the distance to Alpha Centauri. If we could line up Earths and moons between here and our stellar neighbour, we would need to cross the Earth-Moon gap over and over and over again, day after day, year after year, century after century, for longer than human civilization has existed. Another way to comprehend this distance is through scale. Imagine shrinking the solar system until Earth is the size of a grain of sand. On this scale, the Sun would be a golf ball, and Pluto would orbit about half a mile away. Now, on this same scale, where would Alpha Centauri be? Not across the room, not across the city. Alpha Centauri would be located over 3,000 miles away. The nearest star to our Sun, in a scaled model where our entire solar system fits within walking distance, would be on another continent entirely. This is the void we face, not a gap between worlds, but an abyss between islands of light floating in an ocean of emptiness. The harsh reality becomes clearer when we consider our fastest spacecraft. Voyager 1, launched in 1977, is currently the most distant human-made object in existence. It travels at approximately 38,000 miles per hour, a speed achieved through decades of technological advancement and carefully calculated gravity assists from Jupiter and Saturn. This spacecraft has left our solar system and now drifts through interstellar space, carrying with it a golden record containing sounds and images of Earth, a message to any civilization that might one day find it. Voyager 1 is humanity's fastest ambassador to the stars. At its current velocity, if Voyager 1 were pointed directly at Alpha Centauri, which it is not, it would take approximately 73,000 years to arrive. 73,000 years. When Voyager 1 was launched, the Cold War still gripped the world. Disco music played on radios. Personal computers did not yet exist in most homes. That was less than 50 years ago. Now imagine waiting not 50 years but 73,000. This is not a journey. It is a geological epoch. It is longer than all of recorded human history. When Voyager 1 would finally reach Alpha Centauri, humanity, if it still exists, would be unrecognizable from the species that launched it. The human mind is not equipped to comprehend such timescales. We understand our own lifetimes, perhaps these lifetimes of our grandparents and grandchildren. We can imagine with effort the span of a few centuries. But 73,000 years? It becomes meaningless, a number that slides through our consciousness without leaving an impression. This is the psychological impossibility of interstellar travel. It is not just that the distances are vast, it is that they are vast beyond the capacity of human experience to process. We are creatures of days and seasons, not of millennia and epochs, and yet Alpha Centauri calls to us. It is not a single star, but three, locked in an eternal gravitational dance. Alpha Centauri A and B orbit each other in a binary system, two stars circling a common centre of gravity every 79 years. Alpha Centauri A is slightly larger and brighter than our own Sun, while B is slightly smaller and dimmer. Together they create a double sunset unlike anything visible from Earth, a sky where two suns chase each other across alien horizons. Then there is Proxima Centauri, the third member of this stellar family. Proxima is a small red dwarf, cooler and dimmer than its larger companions, orbiting the binary pair at an immense distance. It is technically the closest star to Earth at 424 light-years, just slightly nearer than Alpha Centauri A and B. And orbiting Proxima is a world that has captured the imagination of scientists and dreamers alike, Proxima Centauri b. This planet exists in what astronomers call the habitable zone, the region around a star where liquid water could theoretically exist on a planet's surface. It is roughly Earth-sized, perhaps 1.3 times our planet's mass. Its year lasts only 11 Earth days, as it orbits tightly around its dim red sun. The possibilities are tantalizing. Could there be oceans on Proxima Centauri b? Could there be an atmosphere? Could life, in some form we recognize or cannot yet imagine, exist on its surface? We do not know. We may never know. Because even though Proxima Centauri b is the closest exoplanet we have discovered in a potentially habitable zone, it remains utterly, absolutely unreachable. To understand the magnitude of this distance, we can compare it to the greatest voyages in human history. Ferdinand Magellan's expedition circumnavigated the Earth, a journey that took 3 years and covered approximately 42,000 miles. The Apollo missions travelled 240,000 miles to the Moon, and back in 8 days. The Voyager spacecraft have journeyed over 14 billion miles from Earth across more than 4 decades. Each of these represents an exponential leap in distance and time, but the leap from our solar system to Alpha Centauri is not merely exponential, it is transcendent. It is not a leap at all. It is a chasm that swallows entire categories of human achievement. Consider the void itself. When we think of travel, we imagine moving through something: air, water, terrain. Even space travel within our solar system involves journeying through a region that contains planets, moons, asteroids, comets, objects we can navigate around, destinations we can aim for. But the space between stars is different. It is not empty in the way a desert is empty, with landmarks and boundaries. It is empty in a fundamental, absolute way. Between our Sun and Alpha Centauri lies nothing. No planets, no asteroids, no oases of matter to break the journey. Only a void so vast and so dark that light itself takes over 4 years to cross it. This is not ocean travel, where currents can carry ships and winds can fill sails. This is not air travel, where the atmosphere provides lift and resistance. Interstellar space is the truest empty. a vacuum punctuated only by the occasional hydrogen atom, stray particles of cosmic dust so diffuse they are barely there at all. There is no medium to push against, no environment to navigate. There is only the inertia you bring with you, and the immense gravitational wells of distant stars pulling at you from unimaginable distances. And even if we could somehow accelerate a spacecraft to meaningful fractions of light speed, communication would become impossible in any practical sense. Radio waves, like all electromagnetic radiation, travel at the speed of light. A message sent from a spacecraft halfway to Alpha Centauri would take over 2 years to reach Earth. The response would take another 2 years to return. A simple conversation, a question and answer, would require more than 4 years. Mission control could not guide the spacecraft. Instructions could not be sent to adjust course. Any problem encountered would have to be solved autonomously, or it would not be solved at all. The spacecraft would be more isolated than any human traveller in history, a lonely spark of intelligence drifting through darkness, with no possibility of rescue, no hope of guidance, and no connection to home except the faint whisper of radio signals arriving years after they were sent. This isolation is not just logistical, it is existential. A ship travelling to Alpha Centauri would not be exploring in the way Magellan explored, discovering new lands while maintaining the possibility of return. It would be severing itself from humanity entirely, embarking on a journey from which no signal, no data, and certainly no crew could meaningfully return within a human lifetime. Even unmanned probes, sent as our robotic ambassadors, would become ghosts long before they arrived. Their human creators dead for generations, their mission parameters possibly obsolete, their very purpose forgotten by a humanity that had moved on or perhaps ceased to exist. Now we arrive at the most sobering calculation of all, the energy required. To send even a small probe to Alpha Centauri within a reasonable time frame, let's say 40 years, a single human lifetime, requires accelerating it to roughly 10% of the speed of light. This is 67 million miles per hour. At this velocity, the kinetic energy required is staggering. For a probe weighing just 1 ton, the energy needed would be equivalent to thousands of nuclear weapons, more energy than most nations produce in a year, focused entirely on accelerating a single small object. And that is only the acceleration phase. To stop at Alpha Centauri, to enter orbit around Proxima Centauri b, and conduct observations, the probe would need to decelerate. This requires nearly the same amount of energy again. Unless the probe simply flies past its destination at 10% of light speed, snapping a few photographs during a brief encounter lasting hours or minutes before vanishing back into the cosmic void, it must carry enough fuel to slow itself down. But fuel has mass, and mass requires more energy to accelerate. The equation becomes a recursive nightmare, each solution demanding exponentially more energy than the last. Even with theoretical technologies like nuclear pulse propulsion, where nuclear explosions propel a spacecraft forward, or antimatter engines which convert matter directly into energy, the requirements remain almost insurmountable. Antimatter, the most energy-dense fuel theoretically possible, does not exist in large quantities anywhere in the universe that we can access. It must be manufactured particle by particle at enormous cost. Producing enough antimatter to fuel an interstellar probe would require the entire energy output of human civilization for years, perhaps decades, focused on a single mission. The tyranny of distance is not merely that Alpha Centauri is far away. It is that every light year represents not just distance, but energy, time, isolation, and the limits of human comprehension. It is that the universe is structured in such a way that stars are separated by voids so immense that even light, the fastest thing that exists, takes years to cross them. And we, bound by the laws of physics, made of matter that cannot be accelerated without immense energy expenditure, find ourselves trapped not by lack of ambition, but by the fundamental architecture of space-time itself. As we stare up at the night sky and see Alpha Centauri's faint gleam among the stars, we must understand that what we are seeing is not a destination. It is a monument to impossibility, a reminder that the universe is not built for travellers. The distances between stars are not challenges to be overcome with better rockets or more determination. They are barriers woven into the fabric of reality itself, distances so profound that they transform the very meaning of the word travel into something abstract, something that belongs not to human experience but to the cold mathematics of an indifferent cosmos. And yet, knowing this, we continue to look, we continue to wonder. Because even tyranny, even impossibility cannot entirely silence the ancient human urge to reach beyond the horizon, to touch what lies just out of reach, to dream of crossing the uncrossable void. Distance is only half the story. The other half is written in the language of energy, and it speaks of impossibilities that mathematics cannot ignore. When we imagine reaching Alpha Centauri, we instinctively think of rockets. After all, rockets carried us to the moon. They delivered probes to every planet in our solar system. They are humanity's answer to gravity, our mechanical wings that lift us beyond the atmosphere. But there is a problem, one so fundamental that it undermines every conventional dream of interstellar travel. The rocket equation does not bend. It does not compromise. And when we apply it to the distances between stars, it reveals a truth we would rather not hear. We cannot simply fuel our way to Alpha Centauri. The energy required transcends possibility itself. The rocket equation, first formalized by Konstantin Tsiolkovsky in 1897, is deceptively simple. It describes the relationship between a rocket's velocity, the amount of fuel it carries, and the speed at which that fuel is expelled. As velocity increases, the amount of fuel needed grows exponentially, not linearly. This means that to go twice as fast, you do not need twice the fuel. You need exponentially more. And as we approach speeds necessary for interstellar travel, the fuel requirements do not just become impractical. They become absurd, then impossible, then finally laughable in their magnitude. Consider what it would take to accelerate a spacecraft to just 10% the speed of light, a modest velocity by interstellar standards. Even at this speed, the journey to Alpha Centauri would take over 40 years. Yet to reach even this fraction of light speed using chemical rockets, the kind that launched Apollo and the space shuttle, would require fuel equal to more mass than exists in the entire solar system. Not just the planets. Everything. Every asteroid, every comet, every particle of dust orbiting the sun. This still would not be enough. The rocket equation demands more than the universe can provide. This is not a limitation of current technology. It is not a problem waiting for better engineers or smarter designs. It is a mathematical wall built into the fabric of physics itself. Chemical propulsion is fundamentally irrevocably inadequate for interstellar travel. The energy density of chemical fuels, the amount of energy stored per unit of mass, is simply too low. Burning hydrogen and oxygen, the most efficient chemical combination we know, releases energy measured in thousands of joules per kilogram. To cross light years, we need energy measured in billions, trillions, quadrillions of joules. Chemical rockets are not slow because they are primitive. They are slow because chemistry itself cannot contain the power we need. So we turn to alternatives. Ion drives, electric propulsion systems that accelerate particles using electromagnetic fields rather than combustion. These engines are marvels of efficiency. They can operate for years, slowly accelerating spacecraft to velocities impossible for chemical rockets. NASA's Dawn mission used ion propulsion to visit the asteroid belt, and its success seemed to hint at a future where electric engines might carry us farther still. But even ion drives falter before the immensity of interstellar space. Their thrust is measured in fractions of a newton, barely enough to feel if you held the engine in your hand. To accelerate a crude spacecraft to even a fraction of light speed would take not decades, but centuries, perhaps millennia. The efficiency of ion drives is elegant, but their power is minuscule. They can whisper us through the solar system, but they cannot scream us toward the stars. Then there is nuclear propulsion, the threshold where science fiction begins to touch reality. Project Orion, conceived in the 1950s, proposed a spacecraft propelled by nuclear explosions. The design was audacious: detonate atomic bombs behind a massive shock absorber plate and ride the shockwave like a surfer on a wave of annihilation. Calculations suggested that such a craft could reach 5% the speed of light, enough to make Alpha Centauri reachable within a human lifetime. For a brief moment it seemed possible. The energy was there, the physics worked. But reality intervened in ways both practical and ethical. The radiation released by thousands of nuclear detonations would be catastrophic, not just for the crew, but for any environment the spacecraft passed through. The acceleration forces would be brutal, crushing, requiring suspension systems and shielding that pushed the boundaries of material science. And perhaps most damning, the project required detonating nuclear weapons in space, a proposition that became politically and morally untenable. Project Orion was shelved, not because it could not work, but because the cost of making it work was unacceptable. The dream lingered, but the radiation and violence required to achieve it ensured it remained only a dream. Nuclear fusion offered a gentler alternative. Instead of bombs, controlled fusion reactions could propel spacecraft with immense power and far less radiation. Fusion rockets could theoretically achieve velocities between 10% and 20% light speed, transforming interstellar travel from impossible to merely improbable. But fusion propulsion carries its own curse. We have not yet achieved sustained, controlled fusion on Earth. Decades of research have brought us closer, but every reactor built so far consumes more energy than it produces. The ignition point, the moment when fusion becomes self-sustaining, remains tantalizingly out of reach. We cannot power cities with fusion, let alone spacecraft. Until that changes, fusion propulsion is a promise written in equations but not yet forged in metal and fire. Some visionaries imagined a solution even more elegant: the Bussard ramjet. Proposed by physicist Robert Bussard in 1960, the concept was breathtaking in its simplicity. Instead of carrying fuel, why not gather it along the way? Space is not empty. Even in the interstellar void, hydrogen atoms drift in trace, amounts roughly 1 atom per cubic centimetre. A spacecraft equipped with an enormous magnetic scoop, hundreds or thousands of miles wide, could funnel this hydrogen into a fusion reactor, using the very substance of space as propellant. The ramjet would accelerate continuously, never running out of fuel, limited only by the density of the interstellar medium. It was beautiful. It was clever. It was impossible. The engineering challenges are overwhelming. The magnetic scoop must be vast beyond comprehension, requiring energy to maintain fields spanning distances greater than entire planets. The hydrogen collected must be compressed and ignited in a fusion reactor that, again, does not yet exist. And most critically, the drag created by the magnetic field interacting with interstellar particles may exceed the thrust generated by the fusion engine. Instead of accelerating, the ramjet could slow itself down, trapped by the very medium it sought to exploit. The Bussard ramjet remains one of the most elegant ideas in propulsion theory, but elegance does not overcome physics. The concept endures in textbooks and speculative papers, a monument to human ingenuity and the universe's indifference. If conventional fuels and fusion fail, perhaps the answer lies in the most energetic reaction known to physics: matter-antimatter annihilation. When matter and antimatter meet, they destroy each other completely, converting 100% of their mass into energy according to Einstein's famous equation, E equals mc squared. No other reaction is more efficient. A single kilogram of antimatter, annihilated with a kilogram of matter, releases energy equivalent to 43 million tons of TNT. With antimatter propulsion, reaching significant fractions of light speed becomes theoretically possible. The fuel requirements shrink from impossible to merely staggering. This is the dream fuel, the ultimate source of energy, but antimatter is not found in nature. It must be created particle by particle in massive accelerators like those at CERN. The process is staggeringly inefficient. For every antimatter particle produced, billions of times more energy is consumed than the particle itself contains. At current production rates, creating a single gram of antimatter would take approximately 100 billion years and consume more energy than human civilization has generated in its entire history. Even if production improved by factors of millions, we would still face the problem of storage. Antimatter cannot touch normal matter, or it annihilates instantly. It must be contained in magnetic traps, suspended in perfect vacuum, isolated from every atom around it. A containment failure, even for a fraction of a second, results in an explosion. Antimatter propulsion offers perfect efficiency in theory, but the gulf between theory and practice is measured in impossibilities we cannot yet bridge. Perhaps the answer is not to carry fuel at all. Solar sails and laser-driven light sails propose a different approach, use light itself as propulsion. A thin reflective sail, kilometers wide, catches photons from the sun or a powerful laser array. Each photon imparts a tiny amount of momentum, and over time, these accumulated pushes accelerate the sail to remarkable speeds. The concept is real. Japan's Ikaros probe successfully demonstrated solar sail technology in 2010, and the idea has captured imaginations ever since. The Breakthrough Starshot initiative proposes using this method to reach Alpha Centauri within a human lifetime. A tiny spacecraft no larger than a microchip, equipped with a light sail, would be accelerated by an array of ground-based lasers. These lasers, collectively generating gigawatts of power, would push the sail to 20% the speed of light in a matter of minutes. The journey to Alpha Centauri would take only 20 years. It sounds miraculous, and in some ways it is. But miracles come with caveats. The spacecraft must be impossibly small and light. There is no room for humans, no space for cargo, barely enough mass for a camera and transmitter. The laser array required would be one of the largest construction projects in human history, consuming power equivalent to entire nations. And most troubling of all, there is no way to slow down. A spacecraft pushed by lasers from Earth will arrive at Alpha Centauri at 20% light speed and keep going, passing through the system in a matter of hours. To capture data, to orbit, to explore, the craft must decelerate, and there is no mechanism to do so. The destination becomes a blur, glimpsed and gone, a flyby measured in moments. Breakthrough Starshot offers us a postcard from another star, but not a journey. It is a message in a bottle flung into the cosmic ocean. Every propulsion method we conceive crashes against the same insurmountable barrier: energy. The faster we wish to travel, the more energy we need, and the relationship is not linear but exponential, then relativistic, then absurd. Carrying fuel multiplies the problem because fuel has mass, and accelerating that mass requires more fuel, which adds more mass, which requires even more fuel. It is a recursive equation with no solution. To escape this trap, we must abandon the idea of carrying fuel altogether, but then we lose control. We become dependent on external energy sources, lasers that must remain operational for decades, interstellar hydrogen that may not be dense enough to sustain fusion, or sails that cannot stop. The energy problem is not a challenge waiting to be solved. It is a statement about the universe. It tells us that the distances between stars are not merely far, they are defended by physics itself. Every equation, every propulsion concept, every clever workaround leads back to the same conclusion. Reaching another star requires energy on a scale we cannot generate, cannot store, and cannot sustain. We stand at the edge of our solar system with all the tools of chemistry, electricity, and nuclear, fire, and we find that it is not enough. Not nearly enough. And so we are left with a quiet, unsettling realization. The rockets that carried us to the moon, the probes that explored Jupiter and Saturn, they are marvels of engineering. But they are toys compared to what interstellar space demands. The energy problem does not ask us to build better engines. It asks us to rewrite the rules of physics, or accept that some distances were never meant to be crossed, at least not by beings made of flesh, bound by time, and limited by the energy we can hold in our hands. Even if we solve the impossible energy requirements, even if we somehow build engines capable of pushing a spacecraft to a meaningful fraction of light speed, we encounter something far more fundamental, far more insurmountable. The laws of physics themselves become our adversary. Einstein's equations, elegant and beautiful in theory, transform into instruments of cosmic torture when applied to interstellar travel. At relativistic speeds, the universe itself changes, time fractures, space warps, matter becomes energy, and the void between stars, once empty and benign, becomes a storm of lethal radiation waiting to tear apart anything foolish enough to move through it at such velocities. This is where optimism dies, not in engineering challenges or budgetary constraints, but in the fundamental architecture of reality itself. To reach Alpha Centauri in a human lifetime, we must confront Einstein, and Einstein, as we will see, does not negotiate. The first nightmare arrives softly, almost poetically. Time dilation. According to Einstein's special relativity, as an object approaches the speed of light, time slows down for that object relative to a stationary observer. This is not science fiction. It is proven, measurable, and absolute. At modest speeds, the effect is negligible. But as velocity increases toward light speed, time begins to fracture in ways that shatter the concept of a shared human experience. Imagine a spacecraft accelerating to 50% the speed of light, 0.5 c. For those aboard the vessel, time passes normally. They age, they eat, they sleep, they watch the stars drift by outside their windows. But back on Earth, time moves faster. The crew's biological clocks tick slower relative to those left behind. A journey to Alpha Centauri that takes 10 years for the travellers might see 15 or 20 years elapse on Earth. The gap widens with every increment of speed. At 70% light speed, the distortion becomes severe. Time aboard the ship slows to roughly 70% of Earth time. A decade for the crew becomes 14 years for everyone else. At 90% light speed, time dilation becomes extreme. 10 years aboard the ship equals more than 20 years on Earth, and at 99% light speed, approaching the theoretical limit, time nearly stops. A journey that feels like 5 years to the travellers could see 50 years. Pass on Earth, perhaps more. This is not a technical problem to be solved. It is a severing of human connection across time itself. The crew that departs will return to a world they no longer recognise. Everyone they knew will have aged decades beyond them. Children will have grown old. Loved ones will have died. Civilizations will have evolved. The travellers become temporal refugees, displaced not in space but in time, forever separated from the moment they left. There is no reunion, only loss stretched across the years. But time dilation is only the beginning. As velocity increases, space itself begins to warp. Length contraction, another consequence of relativity, causes distances in the direction of travel to compress from the perspective of the moving observer. At half-light speed, the contraction is modest, but at 90% light speed, distances shrink to less than half their resting length. At 99%, space compresses to a fraction of its original dimension. Alpha Centauri, 4.37 light-years away, might appear to be only 1 light-year distant from the perspective of the ship. This sounds advantageous. A shorter journey. But length contraction is an illusion of perspective, not a reduction in actual distance. The universe outside the ship continues unchanged, and this warping of space introduces nightmarish complications for navigation, perception, and survival. The stars themselves shift position. Light from ahead blue shifts into harsh ultraviolet and X-rays. Light from behind red shifts into dim infrared, fading toward invisibility. The cosmic background radiation, the faint afterglow of the Big Bang, warps into a blinding wall of high-energy particles directly ahead. The universe ceases to look like the universe. It becomes a distorted, unrecognizable hellscape of compressed space and lethal radiation. And then comes the third nightmare, the one that transforms the empty vacuum of space into a firing squad. At everyday speeds, interstellar space is nearly empty. A few hydrogen atoms per cubic centimetre. Dust grains separated by miles. Harmless. Invisible. But at relativistic velocities, even a single hydrogen atom becomes a bullet. At 50% light speed, a hydrogen atom striking the hull of a spacecraft carries kinetic energy equivalent to a grain of sand moving at several thousand miles per hour. At 90% light speed, each atom impacts with the energy of a high-velocity rifle round. At 99%, they become particle beams, their kinetic energy skyrocketing into ranges normally seen only in particle accelerators. Consider a grain of sand, tiny, insignificant, a speck weighing perhaps 1 milligram. At half the speed of light, that grain carries kinetic energy exceeding 10 million joules. Enough energy to vaporize steel, enough to punch through meters of solid material in an instant. A grain of sand becomes a miniature nuclear explosion. Now multiply that by the billions of dust particles scattered through interstellar space. Every cubic kilometre the ship passes through contains countless such grains, each one a potential catastrophe. Shielding seems like the obvious solution. Build thicker armour, layer the hull with meters of dense material. But here, physics tightens the noose again. The mass required to shield against relativistic impact scales exponentially. A shield capable of stopping high-velocity particles must be incredibly thick, incredibly dense, and therefore incredibly massive. Adding mass to the spacecraft makes it harder to accelerate, which requires more energy, which requires more fuel, which adds more mass. The equation spirals into impossibility. Every kilogram of shielding demands exponentially more energy to move, and at relativistic speeds, even a small increase in mass becomes catastrophic. This brings us to perhaps the cruelest aspect of relativistic travel. Mass increase. Einstein showed that as an object approaches light speed, its relativistic mass increases. Not its physical size, but its resistance to further acceleration. The faster you go, the harder it becomes to go faster still. At 90% light speed, the effective mass of the ship is more than double its rest mass. At 99%, it increases by a factor of 7. At 99.9%, more than 20 times. This means that accelerating a spacecraft from 90% light speed to 95% requires vastly more energy than accelerating from 0 to 90%. The energy curve becomes vertical. Approaching true light speed demands infinite energy, not impractically large energy, not theoretically vast energy, infinite energy. The universe itself does not contain enough energy to accelerate even a single atom to exactly light speed. This is why light speed is called a limit. It is not a speed barrier to be broken. It is the edge of physical possibility, a wall built into the structure of reality itself. But the nightmares deepen. At extreme accelerations, even the act of speeding up creates its own form of torment. The Unruh effect, a bizarre prediction of quantum field theory, suggests that an accelerating observer experiences what appears to be a thermal radiation bath. An observer undergoing constant acceleration would detect a faint glow of particles appearing from the vacuum itself, as if space were warming up around them. At modest accelerations, this effect is negligible, undetectable. But at the sustained, brutal accelerations required to reach relativistic speeds within reasonable time frames, the Unruh radiation could become significant. The ship would be bathed in a low-level thermal glow, not from external sources, but from the act of acceleration itself. Heat generated by motion through space-time, another burden, another unsolvable problem layered upon all the others. Navigation becomes another relativistic nightmare. At rest, or at modest velocities, navigation is straightforward. Measure star positions, calculate trajectories, adjust course as needed. But at 90% light speed or higher, the universe ceases to cooperate. Starlight from ahead compresses and blue, shifts into the ultraviolet and X-ray spectrum. The familiar constellations vanish, replaced by harsh radiation, invisible to human eyes and lethal to human tissue. Stars behind the ship red shift into deep infrared, fading toward invisibility. The cosmic microwave background radiation, normally a uniform glow at microwave frequencies, concentrates ahead of the ship and shifts into visible light, then ultraviolet, then X-rays, forming a brilliant and deadly wall of radiation directly in the path of travel. This is not merely inconvenient, it is blinding. Instruments designed to navigate by starlight fail. The familiar reference points of the cosmos distort beyond recognition. A ship travelling at near light speed would effectively be flying blind, unable to see ahead, unable to navigate by traditional means, surrounded by a universe transformed into something alien and hostile. Compensating for these distortions requires computing power and predictive models so advanced they verge on the impossible. One miscalculation, one error in trajectory correction, and the ship could drift off course by light years, missing its target entirely, doomed to wander the void until fuel and life support run dry. And then, the final nightmare. Cosmic rays. At rest, Earth is protected by its magnetic field and atmosphere, shielding us from the constant bombardment of high-energy particles streaming through space. In the depths of interstellar space there is no such protection. Cosmic rays, protons and heavier nuclei, accelerated to near light speed by supernovae and other violent cosmic events, permeate the galaxy. At modest velocities, shielding can reduce exposure to manageable levels. But at relativistic speeds, the situation inverts. The faster the ship moves, the more cosmic rays it encounters per unit time. From the ship's perspective, space itself becomes denser with radiation. A spacecraft travelling at 90% light speed effectively increases its exposure to cosmic radiation by a factor of several times baseline levels. At higher speeds, the effect intensifies. Cosmic rays strike the hull, penetrate shielding, and flood the interior with secondary particles, neutrons, pions, gamma rays. These particles tear through human tissue, shredding DNA, damaging cells, inducing cancers, degrading neural tissue. Even with the best shielding imaginable, prolonged exposure at relativistic speeds would deliver radiation doses far exceeding safe limits. The crew would sicken. Their cells would fail. Their bodies would break down not from age, but from the accumulated violence of high-energy particles ripping through them day after day, year after year. There are no easy solutions. Water shielding, hydrogen-rich polymers, magnetic deflection. Systems. Each offers marginal protection at the cost of enormous mass and energy. None can eliminate the threat entirely. At relativistic speeds, the universe itself becomes hostile to biology. Life, evolved in the gentle cradle of planetary surfaces, cannot endure the radiation environment of near light speed travel. We are not built for this. Our cells, our DNA, our fragile organic machinery, all of it fails under the relentless assault of high-energy particles. To travel at the speeds necessary to reach Alpha Centauri in a human lifetime is to sentence the crew to a slow death by radiation, even if every other problem could somehow be solved. Each of these nightmares alone is nearly insurmountable. Together, they form an interlocking web of physical constraints that crush the dream of relativistic interstellar travel. Time dilation severs human connection across decades. Length contraction and light distortion make navigation nearly impossible. Interstellar dust becomes a storm of kinetic death. Mass increase makes acceleration exponentially harder. The Unruh effect adds thermal torment to sustained acceleration. Cosmic rays flood the ship with cellular destruction. And underlying it all is the fundamental equation of relativity, beautiful and merciless, stating clearly that light speed is not a goal to be reached, but a boundary that cannot be crossed. Einstein is not merely a challenge, he is the final word. His equations do not bend, they do not compromise, they describe the universe as it is, not as we wish it to be. And they tell us with mathematical certainty that reaching Alpha Centauri at relativistic speeds is not just difficult, it is a journey into nightmare, a voyage where time, space, matter, and energy conspire against survival, where every solution creates two new problems, where the faster we go, the more hostile the universe becomes. To attempt such a journey is to fight reality itself, and reality, as we have learned again and again, always wins. The dream of stepping onto a world orbiting Alpha Centauri within a human lifetime crashes not against the limits of technology, but against the immovable foundations of physics. Einstein becomes our enemy not by choice, but by the simple, undeniable fact that the universe operates according to his rules, and his rules say no, not now, not ever. Not at the speeds required to make the journey meaningful to the fragile time-bound creatures we are. Ahead lies another question. If we cannot go fast, perhaps we can go slow. But that introduces an entirely different set of horrors. The generation ship. A vessel that must carry not individuals but entire lineages across the void. And as we will see, the technology is not the problem. Humanity itself is. If we cannot travel fast enough to reach Alpha Centauri within a human lifetime, then perhaps the solution is not to arrive within a lifetime, but across many. The generation ship emerges as humanity's most realistic option for interstellar travel, a vessel so vast it becomes a world unto itself, carrying not just passengers, but entire civilizations across the void. These ships would need to sustain human life for centuries, perhaps millennia, as generation after generation is born, lives, and dies between the stars. Children would grow old, never having seen Earth, knowing it only through stories and archived images. Their children would consider the ship itself as home, the metal corridors and artificial gardens as natural as forests and rivers once were to their ancestors. The concept is elegant in its simplicity. If we cannot shorten the journey, we extend the travellers. Yet, as we examine this solution more closely, a troubling paradox emerges. The generation ship is not defeated by physics or engineering alone, but by biology, psychology, and the fragile nature of human society itself. In attempting to carry humanity to the stars, we discover that humans may be the weakest link in the entire endeavour. Building a generation ship requires solving problems that stretch far beyond propulsion and life support. First among them is the question of population. How many people must we send to ensure genetic diversity across centuries of isolation? The answer is not dozens or hundreds, it is thousands. Population geneticists have calculated that a minimum viable population to avoid the catastrophic effects of inbreeding and genetic drift would require between 10,000 and 40,000 individuals. This is not a crew, this is a city. And it must be a city that functions perfectly, without resupply, without outside contact, without the ability to escape or seek help for hundreds of years. Consider what this means in practical terms. A population of 10,000 people requires food production on a scale that challenges our most advanced agricultural systems. It requires water recycling so efficient that not a single molecule can be wasted. It demands air purification, waste management, medical facilities, schools, governance structures and social systems all functioning flawlessly within the confines of a closed metal environment hurtling through the void. There is no margin for error. A single catastrophic failure in any system could doom the entire mission. And unlike Earth, where ecosystems have evolved over billions of years to achieve balance, a generation ship's artificial ecosystem must achieve that balance immediately and maintain it indefinitely. The psychological challenges are even more daunting. Research on human behavior in isolated and confined environments reveals patterns that are deeply troubling for long-duration space missions. Studies of Antarctic research stations, submarines, and space stations consistently show that even highly trained, carefully selected individuals begin to experience psychological stress, social conflict, and behavioral changes after just months of isolation. Extend that timeline to centuries, and the probability of social collapse becomes not just likely, but inevitable. Imagine the reality of life aboard such a vessel. You're born inside metal walls. You grow up knowing that every breath you take is recycled. Every drop of water you drink has passed through countless bodies before yours. You look out windows not at landscapes, but at the unchanging darkness of space, perhaps with a single distant star growing imperceptibly brighter over decades. The sun that warmed your ancestors is now just another point of light, indistinguishable from 1,000 others. There is no wilderness to explore, no new horizons to discover. Your world is mapped, catalogued, and utterly finite. Generation after generation would face a question that erodes the foundation of the mission itself. Why continue? The people who launched this journey had Earth to leave behind and a new world to dream of reaching, but the middle generations have neither. They inherit a mission they did not choose, endure hardships for a destination they will never see, and must convince their children to do the same. Across centuries, cultures drift. Language evolves. Social structures transform. The original purpose of the mission, once clear and urgent, becomes mythology, then perhaps mere tradition, and finally, potentially, forgotten superstition. Historical precedents offer little comfort. Human history is filled with isolated colonies that collapse despite having the immense advantage of being on Earth, with breathable air, drinkable water, and the theoretical possibility of rescue or resupply. The Roanoke colony vanished without explanation. Easter Island's civilization destroyed itself through resource depletion. Remote island populations have repeatedly suffered genetic bottlenecks, social collapse, and extinction. And these failures occurred with access to sunlight, gravity, and an atmosphere, advantages a generation ship cannot offer. Then there is the weight equation, a mathematical and philosophical trap that undermines the very concept of launching a generation ship. Consider this scenario. We launch a generation ship today using current or near-future technology. The journey to Alpha Centauri takes 1,000 years, but technology continues to advance on Earth. 300 years after the first ship launches, humanity develops propulsion systems twice as efficient. They launch a second ship. 500 years after the original launch, a breakthrough in fusion or antimatter propulsion allows ships to travel at a significant fraction of light speed. A third ship departs. The original pioneers, faithfully maintaining their mission across generations, finally approach Alpha Centauri after a millennium of travel. As they prepare to celebrate their arrival and begin humanity's first interstellar colony, they detect signals. There are already humans there. Ships launched centuries after theirs have arrived first. The pioneers are obsolete before they even complete their mission. Their sacrifice was meaningless. This is the cruel mathematics of exponential technological growth applied to interstellar timescales. Launching too early guarantees failure. Waiting guarantees that the journey may never be necessary. There is no optimal launch window because the window is always in the future. The engineering challenges of maintaining a closed ecosystem for centuries compound the human problems. On Earth, ecosystems are unimaginably complex, with millions of species interacting in ways we still do not fully understand. A generation ship must replicate these functions with a fraction of the species, a fraction of the space, and zero tolerance for failure. We would need to cultivate crops in artificial environments, recycle waste into nutrients with perfect efficiency, and maintain air quality without the vast atmospheric buffer that Earth provides. Consider the problem of soil. On Earth, healthy soil is a living system containing bacteria, fungi, worms, and countless microorganisms. These organisms break down organic matter, fix nitrogen, and maintain the chemical balance necessary for plant growth. A generation ship cannot carry Earth soil in sufficient quantity. It must create and maintain artificial soil, which means understanding and replicating processes that take nature centuries. A single imbalance, a pathogen that eliminates a crucial bacteria species, or a pest that targets a food crop could trigger cascading failures throughout the ecosystem. And unlike Earth, where nature can recover given time, a generation ship has no such buffer. Starvation becomes extinction. Radiation presents another seemingly insurmountable obstacle. In the void between stars, cosmic rays and high-energy particles bombard everything in their path. On Earth, we are protected by a magnetic field and a thick atmosphere. A generation ship has neither. To shield its inhabitants from radiation that would cause cancer, genetic damage, and death requires surrounding the living spaces with meters of material, water, rock, metal, or specialized shielding. This adds tremendous mass to the vessel, which in turn requires more fuel, which adds more mass, which requires more fuel. The tyranny of the rocket equation applies even to generation ships. The more we protect the crew, the heavier the ship becomes, and the harder it is to accelerate. Some designs propose spinning the ship to create artificial gravity, essential for preventing bone loss and muscle atrophy over generations. But a spinning habitat introduces mechanical stress on every structure, creates complex maintenance requirements, and demands redundant systems that must function without failure for centuries. A single bearing failure, a crack in a structural member, a malfunction in the rotation control system, any of these could transform the ship from a haven into a tomb. And then there is the question of governance. Who makes decisions aboard a generation ship? The original crew selected on Earth had a mission and a chain of command. But what happens 50 years into the journey when everyone who remembers Earth is dead? Who has authority? How are disputes resolved? How are resources allocated? On Earth, dissatisfied populations can emigrate, revolutionize, or reform. On a generation ship, there is nowhere to go. Social tensions that might disperse naturally in an open society become concentrated and potentially explosive in confined spaces. History shows that even small groups in isolation often fracture into factions. Scale that to thousands of people over centuries, and conflict becomes inevitable. Cultural drift is not merely likely, it is guaranteed. Languages evolve, values shift. The culture that arrives at Alpha Centauri will bear little resemblance to the one that departed Earth. The arriving civilization may not even remember why the journey began. They may have developed entirely new religions, social structures, and purposes. They may view their ancestors' mission as irrelevant superstition, or they may have splintered into factions with fundamentally incompatible worldviews, turning the ship into a battlefield rather than a vessel of hope. Consider also the psychological burden placed on each generation. The first generation volunteers. They understand the sacrifice and accept it willingly, but the second generation is born into a mission they did not choose. The 10th generation lives and dies for a goal that is abstract at best. How do you maintain morale, purpose, and social cohesion across timescales longer than any civilization has ever endured? The ancient Egyptians built monuments that lasted millennia, but even their civilization rose, transformed, and fell. A generation ship mission must exceed that timescale while maintaining technological and social stability without the resources or flexibility that Earth provided. Then there are the scenarios we cannot predict. What happens if a better propulsion system is developed during the journey? Do the travellers continue, knowing they could return to Earth in a fraction of the time it would take to reach their destination? What if they encounter evidence of other intelligence, altering the mission's purpose? What if a faction decides the mission itself is immoral or futile? On Earth, such philosophical disagreements are debated. On a generation ship, they could lead to mutiny, sabotage, or civil war, with nowhere to escape the consequences. Medical challenges present yet another layer of complexity. A generation ship needs not just doctors, but the ability to manufacture medicine, perform surgeries, and treat conditions that may not even exist yet. Genetic disorders could emerge from the limited gene pool despite careful selection. New diseases could evolve in the closed environment, and the ship must carry the knowledge and tools to address all of this without access to Earth's medical infrastructure, pharmaceutical industries, or research institutions. A single epidemic could devastate the population, and unlike Earth, there is no neighbouring region unaffected by the disease to provide aid. The generation ship is humanity's answer to the impossible distances between stars, but in solving the problem of distance, it creates a catalogue of human vulnerabilities. We are creatures evolved for a single planet, adapted to open skies, natural cycles, and social structures that assume space to expand, resources to exploit, and the possibility of failure followed by recovery. A generation ship offers none of these. It is a test of human endurance at scales we have never approached, a bet that our psychology, our biology, and our social structures can remain stable across timescales that dwarf civilizations. In the end, the generation ship reveals a profound truth. The journey to Alpha Centauri is not merely hindered by physics or engineering, it is hindered by us. We are fragile, mortal, social creatures bound by psychological needs and biological limitations that make us spectacularly unsuited for the vast emptiness between stars. The generation ship, our most realistic option for interstellar travel, may ultimately be impossible not because we cannot build it, but because we cannot survive it. The paradox is complete. To reach the stars, we must send humans, but humans are the very reason we cannot get there. When the conventional paths forward become impassable, the human mind turns to innovation, to radical solutions that seem plucked from science fiction. If we cannot conquer distance with speed, perhaps we can conquer time itself. If human bodies are too fragile for the journey, perhaps we can transform what it means to be human. These alternative approaches to reaching Alpha Centauri are elegant, imaginative, and profoundly seductive. Yet each one, when examined closely, reveals not a solution but a transformation of the problem, a new set of impossibilities wrapped in the attractive guise of possibility. The most immediately appealing concept is cryogenic suspension, the idea of freezing human bodies for the duration of the voyage and reviving them upon arrival. In this vision, the crew would not experience the centuries of travel. They would simply close their eyes near Earth and open them again at Alpha Centauri, as if awakening from a long night's sleep. Time would pass around them while they remained suspended, unchanged, preserved like ancient insects in amber. But biology does not surrender to freezing easily. Water comprises roughly 60% of the human body, and when water freezes, it expands. Ice crystals form sharp edges that puncture cell membranes, tearing apart the delicate architecture of life at the molecular level. The damage is catastrophic and irreversible. Every cell in the human body contains these fragile structures, from neurons in the brain to the tissues of vital organs. Freezing a human being is not like freezing water, it is like freezing a city made of glass. Modern cryonics attempts to circumvent this problem through vitrification, replacing the water in cells with cryoprotective agents that prevent ice crystal formation. The body becomes not frozen but glass-like, preserved in a state somewhere between solid and liquid. Yet even this process causes damage. The chemicals required to prevent ice formation are themselves toxic. The process of replacing bodily fluids is invasive and imperfect, and most critically, no human being has ever been successfully vitrified and revived. The technology remains theoretical, demonstrated in small tissue samples and simple organisms, but never in a complete human body with its trillions of interconnected cells and impossibly complex neural networks. Even if we could perfect the suspension process, revival presents its own nightmare of complexity. Warming must occur uniformly and rapidly to prevent ice crystal formation during thawing. Every system in the body must restart simultaneously. The heart, the lungs, the brain, each dependent on the others, each requiring precise conditions. A single failure in any system during revival would result in death. The margin for error is non-existent. We would be attempting to resurrect the dead, not simply awaken the sleeping. And then there is time itself. Cryogenic suspension would need to preserve the body, not for years, but for centuries or millennia. Radiation would continue to penetrate the spacecraft, slowly damaging DNA even in frozen tissue. Cosmic rays do not distinguish between the living and the suspended. Equipment failures become inevitable over such timescales. Who monitors the sleepers? Who repairs the cryogenic systems when they malfunction? The more we examine cryogenic suspension, the more it reveals itself not as a solution, but as a postponement of death, a fragile hope that stretches across centuries with no guarantee of awakening. Perhaps then we should look not to freezing, but to slowing. Hibernation offers a middle path, a state where metabolism decreases dramatically but life continues. Bears hibernate through winter. Certain species of Arctic ground squirrels can lower their body temperature to below freezing without dying. If we could induce a similar state in humans, reducing metabolic needs by 75% or more, we could extend life support resources dramatically and perhaps allow crew members to survive journeys lasting decades rather than years. Research into induced hibernation has shown promising results in animals. By manipulating neurological pathways and chemical signals, scientists have successfully placed non-hibernating species into hibernation-like states. Yet humans are not bears. Our brains are vastly more complex, our metabolic requirements more rigid. Even minor reductions in brain temperature can cause cognitive damage. Our neurons are exquisitely sensitive to changes in oxygen supply, temperature, and chemical balance. To slow the human metabolism for decades would be to walk a razor's edge between preservation and brain, death. Moreover, hibernation does not stop time. It merely slows it. For a journey to Alpha Centauri lasting thousands of years at any achievable velocity, even hibernating passengers would age and die long before arrival. Hibernation might work for journeys within our solar system, where travel times are measured in years, but for interstellar distances it remains fundamentally insufficient. We cannot slow time enough to matter, and so the mind turns to more radical solutions. If the body cannot make the journey, perhaps the mind can travel without it. Digital consciousness uploading represents the ultimate escape from biological limitation. In this vision, the patterns of thought, memory, and personality that constitute a human consciousness are mapped completely, encoded into digital form and transmitted across space as pure information. No life support needed, no biological fragility, no aging or death. The crew would be patterns of data, experiencing subjective time within a simulated environment, unaware that centuries are passing in the physical universe outside their digital existence. This concept is seductive in its elegance. Information can travel at the speed of light. A digital mind requires no food, no air, no protection from radiation. Upon reaching Alpha Centauri, the transmitted consciousness could be instantiated in a new body, perhaps biological, perhaps mechanical, perhaps something we cannot yet imagine. The journey would be experienced subjectively as instantaneous or as a chosen duration within virtual reality. It seems to solve every problem simultaneously, yet it confronts us with impossibilities both technical and philosophical. We do not currently understand consciousness well enough to map it. The human brain contains roughly 86 billion neurons, each connected to thousands of others, forming trillions of synaptic connections that change constantly. Consciousness may not reside solely in neural connections, but in quantum effects, in the precise chemical environment of each cell, in processes we have not yet discovered. To upload a mind, we would first need to understand what a mind is, a question that has eluded philosophy and neuroscience since their inception. Even if we achieved perfect mapping, we face the fundamental question: is a copy the same as the original? If we create a perfect digital replica of your consciousness, complete with all your memories, personality traits and thought patterns, is that you, or is it merely a copy that thinks it is you? The original consciousness, the one reading these words now, would remain in your biological brain. The upload would be a separate entity, identical at the moment of creation, but immediately beginning to diverge as it has different experiences. This is the ancient ship of Theseus problem applied to consciousness itself. If we send a digital copy of human minds to Alpha Centauri, have humans actually reached Alpha Centauri, or have we merely sent sophisticated simulations that believe they are human? The philosophical implications are profound and deeply unsettling. We might achieve the technical feat of transmitting information across interstellar space, while failing entirely to achieve the goal of human exploration. We would have sent our echoes, not ourselves. There is another approach, one that sidesteps the consciousness question entirely. Instead of sending adult humans, awake or suspended, we could send frozen embryos. Genetic material would be stored in the most compact possible form, protected from radiation, requiring minimal resources. Upon arrival at Alpha Centauri, artificial wombs would gestate the embryos, and artificial intelligence systems would raise the resulting children. Humanity would reach the stars not as travellers but as seeds, sprouting in alien soil. This concept appears practical from an engineering perspective. Embryos are far easier to preserve than adult humans. They require no conscious life support during the journey. The spacecraft can be smaller, lighter, faster. A colony could be established with sufficient genetic diversity to ensure long-term survival. It is efficient, elegant, and deeply horrifying. Consider what we would be creating. Children born without parents, without culture, without connection to the world that sent them. They would be raised by machines, programmed by people they would never meet, based on instructions encoded centuries earlier. These children would be human genetically, but would have no human experiences to shape them. They would be orphans on a cosmic scale, generation zero of a civilization with no ancestors, only designers. The ethical questions multiply endlessly. What right do we have to create humans in this way? How could we program an AI to raise children appropriately when human parenting itself is so complex and imperfect? What happens if the AI systems malfunction? What culture, what values, what stories would these children inherit? They would look back toward Earth, a point of a light in their sky, and know only that they were sent as cargo, as genetic potential, as tools for a purpose conceived by distant strangers. And there is a final, crushing practical consideration. Even embryo colonization requires massive infrastructure at the destination. Artificial wombs, gestation systems, food production, education systems, all of this must function flawlessly for decades as the first generation grows to maturity. The spacecraft must contain not just embryos, but an entire artificial civilization in waiting, robotic systems capable of building habitats, producing resources, and creating an environment where human life can flourish. The mass and complexity requirements begin to approach those of sending living adults. We have not escaped the fundamental constraints, we have only transformed them. Perhaps then we should reconsider the entire premise. If human bodies are too fragile and human consciousness too mysterious to transport, why transport matter at all? Why not send information instead? We could transmit complete blueprints for creating human beings, genetic sequences, cultural knowledge, technological specifications. We could send instructions for building artificial wombs and educational systems. We could transmit humanity's entire knowledge base, every book, every piece of music, every scientific discovery. The information would travel at light speed, reaching Alpha Centauri in just over 4 years. This approach is technically feasible. We already possess the technology to transmit vast amounts of data across space. We understand human genetics well enough to sequence complete genomes. The information required to reconstruct human civilization, while enormous, is not infinite. A sufficiently powerful transmission could deliver everything needed to create humans and human culture at Alpha Centauri. But this solution reveals perhaps the deepest problem of all. Who receives this information? Who builds the artificial wombs and gestates the embryos? Who raises the children according to the transmitted instructions? If the answer is no one, then we're simply broadcasting information into empty space, hoping that something or someone at Alpha Centauri happens to be listening and happens to care enough to reconstruct our species from transmitted blueprints. This is not exploration. This is a message in a bottle cast into an ocean that may contain no shores. If the answer is robotic systems we send ahead, then we have not escaped the problem at all. We must still send physical matter, still confront the propulsion challenges, still build systems that can function autonomously for centuries. The information-based approach simply shifts the burden from sending humans to sending the infrastructure to create humans. The fundamental physics problems remain unchanged, and lurking beneath all these alternative solutions is a common thread. They do not actually solve the core problem. Cryogenic suspension still requires transporting human bodies across impossible distances. Hibernation still requires life support systems. Digital consciousness faces both technical impossibility and philosophical incoherence. Embryo colonization and information transmission require massive destination infrastructure that must somehow arrive before or with the transmitted information. Every creative solution we imagine encounters the same immovable obstacle: the vast distances between stars and the absolute speed limit of light. We can reduce the mass of what we send, we can minimize metabolic requirements, we can encode information in the most compact forms possible, but we cannot make the distance smaller, and we cannot make light move faster. The universe does not negotiate. Physics does not compromise. Even our most radical visions of suspended animation, of digital transcendence, of information-based seeding of distant worlds, these are not solutions. They are elaborate accommodations to impossibility, ingenious attempts to reframe the problem so that it appears solvable. They are beautiful dreams that collapse under scrutiny, revealing themselves as variations on the same fundamental theme. The distance between stars is measured not just in light years, but in layers of compounding impossibility. Perhaps the cruelest aspect of these alternative solutions is that they force us to confront what we are willing to sacrifice. Are we willing to send copies instead of ourselves? Are we willing to create orphaned children who will never know Earth? Are we willing to transform the very definition of human existence in order to say that humanity has reached another star? Each solution asks us to abandon something essential, some core aspect of what it means to be human, to achieve a goal that remains, even after these sacrifices, vanishingly unlikely to succeed. The alternatives exist not as viable paths forward, but as measures of our desperation. They reveal how deeply we want to believe that the problem is solvable, that some clever approach, some technology just beyond our current reach, will open the door to the stars, but the physics remains unmoved. the distance remains incomprehensible, and even our wildest dreams of suspended animation and digital transcendence cannot escape the simple, crushing truth that the universe is vast and we are small, and no amount of innovation can change that fundamental equation. Our inability to reach Alpha Centauri is not merely a human limitation. It may be the universe's answer to a question we have asked for decades. Where is everyone? The Fermi paradox, named for physicist Enrico Fermi, poses one of the most haunting questions in all of science. If the universe is so vast, so old, with billions of galaxies each containing billions of stars, many with planets circling in habitable zones, then where are the alien civilizations? Where are the radio signals, the megastructures, the evidence of advanced technology? If intelligent life is common, the galaxy should be teeming with it. We should see signs everywhere, but we see nothing, only silence. Perhaps our struggle to reach Alpha Centauri explains why. Perhaps the distance itself is the answer. The Great Filter hypothesis suggests that somewhere between the emergence of life and the colonization of the galaxy, there exists a barrier so insurmountable that almost no civilization overcomes it. Some filters lie behind us, the jump from chemistry to biology, from simple cells to complex organisms, from life to consciousness. We have passed these thresholds, but perhaps the greatest filter lies ahead, hidden in the void between stars. Perhaps the mathematics of interstellar travel is not just difficult, perhaps it is the boundary where all cosmic ambitions end. If reaching Alpha Centauri is truly impossible for us, despite our technology and determination, then it is likely impossible for everyone. The laws of physics do not bend for anyone. Energy requirements remain absolute. Distances remain unchanged. Time dilation affects all matter equally. If we cannot cross these distances, then perhaps no one can. The silence we hear across the cosmos may not be the absence of intelligence, but the inevitable consequence of interstellar distance itself. Consider what this means. Intelligence may be common. Life may arise on countless worlds, evolving complexity, developing consciousness, building civilizations that peer into their own night skies with wonder and longing. They may reach their own moons, explore their own planets, send probes to the edges of their solar systems. They may solve the mysteries of physics, harness the power of their stars, extend lifespans, cure diseases, achieve wonders we cannot yet imagine. And yet, they remain bound, forever circling their home stars, separated from one another by gulfs that cannot be crossed. Islands of consciousness scattered across an ocean too vast for any bridge. This realization transforms the Fermi paradox from a mystery into a mirror. The silence does not mean we are alone. It means we are isolated. Every civilization, no matter how advanced, may be trapped within its own solar system, looking outward with instruments sensitive enough to detect 1 billion galaxies, but powerless to touch even the nearest star. The universe becomes a cosmic prison where the bars are made not of steel but of light years, where the walls are invisible, yet absolute. Perhaps somewhere, orbiting a red dwarf star 40 light-years away, another civilization gazes toward our sun and faces the same impossible mathematics. They calculate the energy requirements, they understand the timescales, they realize, as we do, that the stars they see in their sky are not destinations but monuments. Beautiful, unreachable, eternal reminders of limits built into the fabric of reality itself. But there exists another possibility, one that shifts the question entirely. Perhaps some civilizations do overcome the physical barriers. Perhaps they develop technologies we cannot yet conceive, methods that circumvent the tyranny of distance and energy. And having achieved this impossible feat, having opened the gateway to the stars, perhaps they choose not to walk through it. Advanced civilizations may discover that physical exploration of the cosmos is vastly inferior to other forms of existence. As technology progresses, the distinction between physical and virtual reality may dissolve. A civilization capable of perfect simulation could explore infinite universes without ever leaving their home system. Every possible world, every conceivable environment, every variation of physics and chemistry could be experienced within computational substrates, more sophisticated than our current minds can imagine. Why endure centuries in the cold darkness between stars when you can experience eternity in realms of your own creation? Why risk the radiation, the isolation, the mechanical failures, when consciousness itself can be freed from the limitations of biology and distance? Physical interstellar travel may be the choice of primitives, those who have not yet realized that the universe within is infinitely larger than the universe without. If this is true, then the galaxy may be filled with civilizations that have turned inward, abandoning the physical cosmos in favor of digital infinities. They orbit their stars in silence, their technology indistinguishable from natural phenomena, their attention focused entirely on interior landscapes. From the outside they would appear as nothing. No radio signals, no expanding sphere of colonization, no visible activity at all, just planets circling stars, as lifeless to our instruments as barren rock, while entire universes unfold in the quantum computations occurring on their surfaces. We scan the heavens for signals, but perhaps the signal stopped long ago, not because civilizations died, but because they transcended the need to reach outward. The final evolution of intelligence may not be expansion across space, but expansion within consciousness itself. Physical reality becomes a starting point, a womb to be outgrown rather than a realm to be conquered. This possibility is both hopeful and deeply unsettling. Hopeful because it means intelligence may be common, that we are not alone in our existence or our questions. Unsettling because it suggests that our dreams of exploring the cosmos, of walking on distant worlds beneath alien suns, may be the dreams of children, ambitions we will abandon once we understand the true nature of existence and experience. Yet there is a darker explanation for the silence, one that requires us to confront the possibility that visibility itself is dangerous. The dark forest hypothesis presents the universe not as an empty wilderness waiting to be explored, but as a forest at night, filled with hunters. Every civilization that arises faces a fundamental problem. They cannot know the intentions of others. Communication across light years takes decades or centuries. By the time you receive a response, the civilization that sent it may have transformed in ways you cannot predict. Trust becomes impossible. Certainty cannot exist. The only safe assumption is that any other civilization might be a threat. In such a universe, the optimal strategy is silence. Make no signals. Build nothing that can be seen from afar. Remain hidden in the darkness, watching, listening, but never revealing your presence. Any civilization that announces itself, that builds beacons or sends messages into the void, marks itself as a target. Not necessarily because space is filled with aggressors, but because even a small chance of aggression, multiplied across billions of potential civilizations, becomes a certainty. One predator in a forest of 1,000 species is enough to make silence the only wisdom. If this hypothesis is correct, then our radio signals, our probes bearing messages and maps showing Earth's location, our very attempts to reach out and touch the cosmos, may be acts of profound foolishness. The great silence may not be absence, but restraint, a universe filled with civilizations holding their breath, hoping not to be noticed by whatever else might be lurking between the stars. The impossibility of reaching Alpha Centauri may be a blessing in this context. If we cannot travel to other stars, then perhaps neither can anything else. The distances that trap us also protect us. The void becomes not a prison but a moat, keeping potential threats at bay as surely as it keeps us confined. Our isolation may be the only reason we still exist. But whether the explanation is physics, transcendence, or predation, the conclusion remains the same. The universe we observe is one where interstellar civilizations, if they exist, do not expand across the galaxy in ways we can detect. The mathematics that makes Alpha Centauri unreachable for us appears to be universal. The filter stands, the barrier holds. This realization demands a profound shift in how we view humanity's future. For centuries, we have imagined ourselves spreading among the stars, colonizing distant worlds, building an interstellar civilization that spans the Milky Way. Science fiction has filled our imaginations with fleets of starships, with federations and empires stretching across thousands of light years. These dreams have inspired generations, driving our technology forward, pushing us to reach beyond our atmosphere. But perhaps these dreams are just that. Beautiful, noble, but ultimately impossible. Accepting this does not mean abandoning ambition. It means redirecting it. If the stars beyond our solar system are forever out of reach, then our cosmic frontier is not interstellar space but our own stellar neighborhood. The solar system itself becomes the canvas for humanity's expansion. 8 planets, hundreds of moons, thousands of asteroids, countless comets in the Kuiper Belt and Oort cloud. Within our sun's gravitational embrace lies more territory than we could settle in millennia. Mars waits to be transformed. Europa and Enceladus hide oceans beneath their ice, potential havens for colonies that could thrive in the darkness. Titan offers a world with atmosphere and lakes, a place where humans might walk beneath alien skies without spacesuits, breathing through masks in air thick enough to fly through with wings. The asteroid belt contains more resources than Earth has consumed in all of human history. Metals, water, minerals, building materials for structures that could house billions. We could hollow out asteroids and spin them to create artificial gravity, building cylinder worlds that rotate through the void, complete ecosystems enclosed in metal and stone. We could construct solar collectors vast enough to power civilizations, fusion reactors fed by helium-3 from the outer, planets, manufacturing centers in the zero gravity of space where materials could be shaped in ways impossible on planetary surfaces. A multi-generational project of solar system colonization could occupy humanity for thousands of years. Each moon explored, each resource tapped, each innovation leading to new possibilities. We would become a solar civilization, spread across a dozen worlds, connected by light-speed communications, diverse in environment yet unified by origin. Our descendants might live on Mars in domed cities watching double moons rise, on floating platforms in Venus's upper atmosphere harvesting wind and sun, in the rings of Saturn where water ice and starlight create landscapes of impossible beauty. This future is achievable, not easy, but possible within the laws of physics we know. The distances are vast by human standards, but measurable in months and years rather than centuries. The energy requirements, while substantial, are within the realm of technologies we are developing. The challenges are engineering problems rather than fundamental impossibilities. If we accept that Alpha Centauri and all the stars beyond are unreachable, we do not diminish ourselves. We find our place. The solar system is not a small domain. Its volume exceeds 10 trillion cubic miles. The energy our sun pours into space every second exceeds all human energy consumption by factors too large to comprehend. We orbit a star that will burn for 5 billion more years, providing light and warmth for eons. Within this sphere lies room for growth beyond anything Earth alone could support. Our cosmic neighborhood becomes both prison and paradise simultaneously. We are confined, yes, bounded by distances we cannot overcome. But we are also gifted with a realm of tremendous potential, a stellar system rich in worlds and resources, lit by a star that makes all life possible. The bars of our cage are also the walls of our garden. Perhaps this is the answer to the Fermi paradox. Not that intelligence is rare, but that every intelligent species reaches the same conclusion we are approaching. The stars are beautiful, the universe is vast, but home, properly defined, is enough, more than enough, A single solar system contains multitudes. A civilization that learns to thrive within its own stellar boundaries may discover that reaching outward was never the goal. The goal was reaching inward, toward deeper understanding of what it means to exist, to think, to build, to endure. We stand at a threshold of recognition. The Alpha Centauri system shines in our southern skies, close by cosmic standards, impossibly far by every practical measure. We have calculated the distance, we have confronted the energy requirements, we have faced the mathematics of relativistic travel and found them insurmountable. This is not defeat, this is clarity. The universe is revealing itself to us not as an infinite frontier waiting to be conquered, but as a structure with limits built into its very fabric. These limits do not diminish the wonder of existence, they define it. They give shape to what is possible and meaning to what we achieve. If we never reach Alpha Centauri, we join a vast invisible community. Every civilization across the cosmos that has looked at its nearest stars and realized the same truth. We are islands, we are bound. We are alone together, separated by distances that cannot be crossed, connected by the shared experience of consciousness in a universe that allows awareness but prevents contact. The silence we hear when we listen to the stars is not emptiness. It is the universe answering our oldest question with absolute honesty. The cosmos is vast. Life may be common. Intelligence may arise on countless worlds. But the space between stars is sacred in its immensity. It remains uncrossed. It will always remain uncrossed. And in accepting this, we find not limitation, but liberation. We stop dreaming of distant horizons and begin building the world that was always within reach, our solar system, our home forever. And so we arrive at the end of our journey, not at the shores of Alpha Centauri, but at the boundaries of possibility itself. We have travelled through calculations and concepts, through relativity and radiation, through generations and galaxies of thought. And what we have discovered is not merely difficult, but impossible. Not because we lack imagination, but because the universe has written laws we cannot rewrite. The barriers are not singular, they are layered, interconnected, absolute. Distance transforms space into an ocean so vast that our fastest spacecraft would take tens of thousands of years to cross it. Energy requirements scale beyond anything we can harvest from stars or matter. Relativity ensures that even if we approach light speed, time itself fractures, severing travellers from everything they know. Biology, fragile and finite, crumbles under the weight of cosmic radiation and the slow decay of generations. And time, indifferent and patient, stretches across eons we cannot survive. Alpha Centauri is not unreachable because we have failed. It is unreachable because the cosmos has dimensions we are not built to traverse. We are creatures of gravity and atmosphere, of soil and sunlight. We evolved on a pale blue world orbiting a single star, and every cell in our bodies remembers that origin. The universe beyond our solar system is not hostile. It is simply indifferent, crafted on scales that do not accommodate human fragility. But this realization is not a defeat. It is a revelation. To accept our cosmic shore is to understand that home is not a limitation. It is a gift. Earth, with its oceans and forests, its storms and seasons, is not a prison from which we must escape. It is the only world in the known universe where life flourishes without intervention, where air can be breathed freely, where water falls from the sky. To know we cannot reach Alpha Centauri is to recognize that we must protect the world we have. There is no backup planet waiting in the darkness. There is only this one, fragile and irreplaceable, suspended in the void. Our solar system, vast and diverse, offers frontiers enough for 1,000 generations. Mars, with its red deserts and ancient valleys, waits to be understood. The moons of Jupiter and Saturn, some harbouring hidden oceans, may hold answers to questions we have not yet learned to ask. Asteroids drift through space carrying metals and minerals beyond Earth's abundance. The Kuiper Belt and Oort clouds stretch outward, unexplored, mysterious, filled with icy remnants from the dawn of time. We do not need to leave our star to become explorers. We need only to recognize that our cosmic neighborhood is larger, stranger, and more wondrous than we have yet imagined. Alpha Centauri will remain where it is, glowing softly in the southern skies, 4 light-years away, and forever beyond our grasp. There is a bittersweet beauty in that distance. It reminds us that some things are meant to be admired, not possessed. Some destinations exist not to be reached, but to inspire us to look upward and wonder. The stars are not goals to be conquered. They are reflections of possibility, scattered across the darkness to remind us that the universe is larger than ourselves. Perhaps, in accepting our limitations, we find our purpose. To build a civilization not obsessed with escape, but devoted to understanding, to thrive within the bounds of our solar system, not for decades, but for millennia. To look at Alpha Centauri and feel not frustration, but gratitude. Gratitude that we live in a universe vast enough to contain mysteries we will never solve, distances we will never cross, wonders we will never touch. Our cosmic shore is not the edge of possibility. It is the beginning of wisdom. Thank you for staying with us through this journey into the impossible. If this exploration has shifted your perspective, even slightly, consider leaving a like and letting us know in the comments where in the world, or perhaps where in the solar system you're listening from. Subscribe for more journeys through science, space, and the quiet mysteries that linger at the edges of sleep. Until next time, may your dreams reach farther than we ever could, into the silent, infinite dark where Alpha Centauri still glows, patient and untouchable, waiting for no one.